So nothing too major today, but I want to just kind of briefly discuss, I guess, one of the big key ideas in integral calculus. And we're going to do that by working with the area of the circle. By the way, what's the area of the circle? Do you guys remember? I hope everyone internally is yelling at themselves pi r squared. And the real question I would like to, I guess, answer is where the fuck does that come from? I mean, we just memorized that as a kid, right? Like, I don't know, in grade 3, I just remembered that it was pi r squared, and I've just known that it's been pi r squared ever since grade 3, but no one's really given me a good explanation of why that's true. So here's our leading question. I know that the area of a circle is pi r squared, but where does that come from? Is there a way that we could potentially have just stumbled into this formula and not really knowing too much about calculus? And the answer is yes. I believe it was a fellow by the name of Archimedes, I believe, was the one that really narrowed this down for us and gave us some really cool kind of introduction to calculus. So if you're into history, Archimedes is the guy you want to look at. And his method of tackling this problem was really interesting. And he arguably invented calculus before Newton and Leibniz. Like, he was pretty good at thinking about things in a very calculus-y based way. So anyway, what we're going to do is we're going to take our circle and we're going to imagine cutting this circle into smaller rings like so. That's actually a pretty good circle. I did good. All right, so what we do is we're going to take that circle, we're going to chop it up into smaller rings, pretending that we've kind of made a slice along the radius, and kind of do our best to stretch that circle out into smaller rectangles. It's not going to be perfect, but here's the basic idea. We're going to take that circle, we're going to take that circle, not bad, I'll work with it. And in green, we're going to create some kind of smaller concentric circles inside, like so. And then we're going to make a cut along the radius. And then I want you to imagine like unraveling that circle. So trying to like take what we get and kind of flatten it out. And we're going to try to arrange it as best we can into the following scenario. So essentially what we want to do is we want to get kind of like this stacked almost like a little pyramid shape. Like pancakes. So it's not going to be perfect, like I said. You know, it's going to be kind of hard, I think, to stretch this out, but we're going to pretend that the circle is stretchy enough that we can kind of form these kind of concentric rings into rectangles. We'll do the best we can. It may not be perfect, but it should be pretty close. Okay, so I guess kind of the idea is I have now just a bunch of rectangles over here, and if I could figure out the area of each one of these little rectangles, I should be able to figure out the area of the circle. So that's the key idea here. If we could sum up the area of all of these small rectangles, that would give us a good approximation of the area of the circle. Log to pyramid, yeah, exactly. And I say good estimation because it's not perfect, right? We're not going to get perfect rectangles when we stretch out the circle. It would be more probably like little trapezoids or something like that. Little rhombuses. I don't know. I forget some kind of, I think trapezoid is the word, right? Some kind of trapezoid. So adding up the rectangles gives us a pretty good estimation for the area. It's not going to be perfect, but we do the best we can. Of course, if you're playing Minecraft, your log looks like this. That's a square joke. Anyway. Okay, let's take a look at one of those particular rings inside of the circle. And let's see if we can't figure out the area of one of those particular rings. So I don't know. I'm going to take one of these, take the highlighter, and let's just take. So it doesn't really matter which ring we take, but I'm going to highlight one. I'm going to pull that ring out of the circle. So one of these kind of center rings like this. And we're going to try to find the area of that highlighted center ring, all right? I don't really know what the new radius is, so I'm just going to call the radius small r. So yes, I'm just going to pull that just out of my butt. What do we know? We know that the radius of the big circle is capital R. So I just want to make sure not to use capital R again. I could use any other kind of variable I want. So let's pretend that the radius of this small circle is small r. Okay, so obviously if we were to cut along that red line and stretch it out, we would get something that looked like this. We get some kind of rectangle, provided it was nice and malleable enough for us to stretch it out into a rectangle. And our goal is to figure out, if I could figure out the length and the width of this rectangle, that might be helpful. And I'm going to do one of those for you. And the other one I want you guys to think about a little bit. So this width, we're going to call this right now, we're going to call it dr. Dr being the differential of the radii. So, or in other words, we can think about it as the difference between the different radii of these concentric rings. Okay, so dr we're going to use as kind of a placeholder. I don't really know how big this is, but essentially it's the difference between two different radii. Now, what about the length of this strip? So hopefully you can see that the width of this strip would be like here, right? The length of this strip would start at the cut and go all the way around the circle. Do you see that in green? I don't know if that's helpful or unhelpful. but that would be the length. So how do I get at the measurement that goes all the way around the circle like that? Do you guys know what that is called? Yeah, exactly. We call that the circumference of the circle. And bonus points for those of you that actually know the formula for the circumference of a circle. What is that? Pi times the 2 pi r? Nice. So key is all over it today. 2 pi r. Yes. So that's going to be the length of this particular strip, 2 pi r. Okay, so those are the two measurements that we need in order to calculate the area of this rectangle, right? Okay, it's just length times width. And so now our goal, knowing this information, is to try to collect all of these rings up together. Okay, and so the next thing that might be helpful for us to know is what's the smallest value we could have for this little r, and what's the largest value we could have for this little r. So what's the smallest radius we might pick for the ring that we choose, and what's the largest r that we could pick for one of these rings? Okay, so I'm just going to zoom out a little bit. I'm asking this question. Instead of maybe this highlighted one here, what if we, I don't know, highlighted the largest outermost circle? What would be little r for that really large outer circle? Well, that really large outer circle has radius capital R. So for that ring that I've highlighted here in pink, the largest possible radius we could have would be capital R. And similarly, if we went like right into the very center here, I'm just drawing a little thing over to the side so I can erase it in a second. But if I took that, like one of those really tiny small circles in the very middle, maybe you could imagine that the smallest radius we might pick would be 0, right? If this circle in the middle was really, really small, there's potential that we could have little r being equal to 0 as well. So we know that this little r must be somewhere between 0 and capital R. So 0 is the smallest radius I could pick. Capital R, since that's the outermost radius of the circle that we're working with, that is the largest value that we could pick. And then what we're going to do is we're going to kind of arrange all of these rectangles onto the XY plane. All right, so we're just going to draw a nice little XY axis, and we are going to have what they call the 2 pi r line. And let's see, let's call this little r. And y would technically be, should be fine. Really need that in there as an extra variable. But anyway, our smallest value for little r is going to be 0, and our largest value for little r we'll put as capital R. And then we know that all of these rectangles that we're trying to find the area for are going to land somewhere in between 0 and capital R. So I'm going to start drawing some examples of these rectangles. Actually, maybe I'll do it in black. Okay, and of course, one of these little chunks here, remember these represent the width of each of our rectangles. This is what we call a dr. So this is a little difference in little r. And of course, the 2 pi r line comes from the fact that each of these, the width, or sorry, the length of each of these rectangles has to be the circumference. Okay, so that's why I'm not pulling this 2 pi r out of nowhere. That's actually the width of these rectangles. So this is kind of what we have. We have some picture that looks kind of like this. And I don't know about you, but it kind of looks like it's pretty close to a triangle. Right, can you guys see that? So it almost looks like a triangle. So I'll kind of highlight what I'm looking at. Like if I filled in all of this in here, it's almost a triangle. I wonder what the area of that triangle is. So imagine that little dr starts getting smaller and smaller, so we start getting more and more rectangles inside of this picture. Eventually, we're going to settle down onto a nice triangle that looks something like this. And this point up here, by the way, is capital R 2 pi capital R. So as we allow this like little dr to get smaller and smaller, we're going to get really good approximations to the area of our circle. And when we actually have a legitimate triangle here, this is going to be probably the best approximation we can get for the area of our circle. And the area of this triangle is base times height over 2. The base length of this triangle is capital R. The height of this particular triangle is 2 pi capital R, and we're going to divide by 2. So simplifying that a little bit, we're going to get pi capital R squared, which is exactly what we expect to see. That is the area of our circle. All right, so just a little bit of a recap. We take a problem, which is finding the area of this really awkward shape. We take the approach of saying, well, if I could break that shape up into smaller rectangles and add up all of the areas of the smaller rectangles, that would be helpful. We do that. we allow one of our differentials to tend towards 0 so that these rectangles become very, very small. Essentially, they become infinitely small. We get a triangle. Area of that triangle ends up being equal to the area of the circle. So this is, I think, a nice kind of introductory section, because I think it gives you a nice overview, I think, of the general problems that we're going to see in our calculus class. So the kind of key takeaways here are, if I'm looking for the area of this really awkward shape, one of the common strategies is to approximate that area with rectangles, because rectangles are easy to find areas of, and we know how to find those areas. And sum up all of those areas, maybe allowing a differential that tends towards 0, and then we get a really good approximation of the actual area. And it's quite surprising, actually, how many different styles of problems in calculus can actually get solved using this shrinking rectangle approach. It's quite fascinating. So that's a nice, hopefully, little introduction for you guys to calculus. I've noted, I don't know if you guys are noticing, but my screen is starting to wobble a little bit. I don't know if you guys can see that or if it's just on my end, but that is, it's starting to make me go a little cross-eyed here. So I know it's time to give my computer a rest. So yeah, if there are no particular questions, we will finish off our class there today, and I will see you guys on Wednesday, and we'll start talking a little bit more about this area problem and how we can, I guess, think about this area problem using derivatives, right? We want to kind of connect it to the concept of the derivative if we can. Yeah, Logan, so these are definitely going to get recorded. I'll upload them later this afternoon. This one's going to be under the area function. So it's just going to be, we're going to post the videos based on the topics, essentially, that we've covered. So yeah, we'll be available to find like last semester. Yeah, no worries, guys. Good to see you again. Hopefully you have a lovely afternoon. Yeah, thanks, Denzel. Have a good one. Yeah, no worries, guys. Thank you very much.